This is the Supermarine Spitfire, a fighter that became an icon for the British Air Force's struggle against the Luftwaffe during World War II. Supermarine used their experience in designing fast racing seaplanes to create a design that was sleek and a thing of beauty, unlike anything else in the sky. We've recreated the Spitfire in minute detail to show how Supermarine turned a racing aircraft into one of the most remarkable fighters in history. In this film, we'll show the Mark I-A production variant that fought during the Battle of Britain. My name is David Webb, and this is Blue Paw Print. The Spitfire Mark I-A was 29 feet 11 inches long and stood 12 feet 8 inches tall. Empty, the aircraft weighed 4,517 pounds. The fuselage was built in 3 sections: the engine section housing the Merlin engine, the main section, and the tail section. The fuselage was an all-metal design. It was built around 4 longerons running lengthwise and 15 ring-shaped frames. The sheer metal outer skin also carried some structural load along with the internal frame. The skin was made from all-clad, an aluminium alloy sheet between a thin layer of pure aluminium bonded to each side to protect against corrosion. Between the frames, small stiffeners were riveted in place first. Then the skin panels were attached to the frames on top of the stiffeners. The surface preparation was meticulous. The skin of the plane was treated with a chemical solution called Dioxidine 202, which cleaned the surface and slightly etched it to help the primer bond. Once the primer was applied, the rivet recesses were filled with putty, and the surface was sanded by hand. A thin coat of paint was then applied with meticulous care so that the finish added as little weight as possible. Techniques from Heinkel's commercial airliners, such as the HE-70, were used to give the Spitfire its smooth surface finish. This technique used on early prototypes was closer to high-end automobile bodywork, with seams filled and rivet lines smoothed to a near mirror surface. But the filler cracked under vibration and could not be maintained at scale. For the mass-produced Mark I-A, flush riveting and labour-intensive careful finishing were kept just on the nose and the wing's leading edges, where smooth surfaces had the greatest effect on speed. The rest of the airframe was finished to a lower standard. The Spitfire's elliptical wing was its most distinctive feature. This shape offered the lowest drag for the amount of lift it generated of any design at the time. The wingspan measured 36 feet 10 inches with a total area of 242 square feet. The wing was exceptionally thin. The thickness to chord ratio describes how tall a wing is compared to how long it is from leading edge to trailing edge. At the root, the Spitfire's wing measured just 13% of its chord in height, roughly 13 inches of actual depth. By the tip, that tapered down to just 6%. At the tip, the Spitfire's wing was nearly twice as thin as the Bf-109E's. The wing was twisted along its length by 2.5 degrees. During a hard turn, the wing roots would stall before the tips, buffeting the pilot while keeping the ailerons responsive. This feel before a stall could prevent inexperienced pilots from losing control at crucial moments. Each wing was built around a main spar. This spar consisted of 2 tubular booms connected by a thick web. The heavy skin on the leading edge combined with the spar to form a rigid D-shaped box. This box carried most of the wing's structural load. The underside of the right wing housed the main coolant radiator in a specially shaped duct. The left wing held the oil cooler with a semicircular fairing and a pitot tube to measure airspeed in flight. Both wings had recesses cut behind the main spar to accommodate retractable landing gear. The elliptical shape meant there were no straight lines. Every panel and spar required complex forming by hand. The production was closer to a luxury car than to a military aircraft. On the downside, it was slow to produce compared to other aircraft with simpler wings, such as the Bf-109. The control surfaces on the Spitfire Mark I-A were built from light alloy ribs and spars, covered in doped linen fabric. The controls were purely mechanical, with no power assist. The ailerons moved 26 degrees up and 10 degrees down. Because of the wing's twist, they remained effective even when the wing root stalled. However, at speeds above 400 miles an hour, the fabric covering ballooned outward from air pressure, causing the ailerons to lock up. To avoid that, later versions used metal-skinned ailerons instead of fabric. The elevators moved 28 degrees up and 23 degrees down. They were highly sensitive and stayed light even during high-speed dives. The rudder moved 28 degrees in both directions. The split flaps were driven by a pneumatic cylinder powered by compressed air. They were used exclusively for landing, acting as air brakes, and only had two positions, up or fully down at 90 degrees. They deployed in just 1 second, and when they did, pilots described the drag as similar to hitting a brick wall. The Spitfire Mark I-A was armed with 8.303 caliber Browning Mark II machine guns, built in Britain under American license. They were mounted entirely inside the wings and placed beyond the reach of the propellers. This eliminated the need for synchronization gears and allowed continuous, unrestricted fire. Each gun carried 300 rounds. Firing all 8 guns simultaneously discharged 160 rounds per second. The recoil was immediate and violent. Pilots described it as instantly scrubbing nearly 25 miles an hour off the aircraft's airspeed. Followed with a sudden nose drop, it felt like the landing flaps had been extended, requiring immediate correction on the stick. During the Battle of Britain, a standard ammunition loadout consisted of 2 guns firing steel-cored armor-piercing bullets, 2 firing older incendiary tracers, 3 guns firing plain ball rounds, and 1 gun loaded exclusively with special Dixon B Mark VI incendiary rounds. The actual bullet was an entirely new design made by Major C. Aubrey Dixon at the Royal Arsenal at Woolwich. The Dixon round contained an incendiary mixture of magnesium aluminium alloy powder and barium nitrate. At the tip of the bullet, a small steel ball sat behind a hard metal anvil. Upon impact, the soft nose of the bullet was crushed inward, driving the anvil back into the ball and igniting the mixture. As a result, the bullet did not ignite until it had penetrated the target, ensuring the mixture ignited preferably inside an enemy fuel tank rather than on the surface. It was roughly twice as effective as older incendiary rounds. The pilot targeted enemy aircraft using the Bar and Stroud Mark II reflector sight, which projected an aiming mark that appeared at infinite distance. This meant the pilot's aim stayed accurate, even if his head shifted slightly in the cockpit. 2 rings at the base set the target range and wingspan. The guns were normally zeroed to 650 yards, although ace pilots often reduced this to 250 yards for denser, more concentrated fire. One of the RAF's leading aces, Adolf Sailor Milan, said, "A 1-second burst of the 8 guns was the equivalent of hurling 240 pounds a minute at a target. A firepower impact which someone likened to a 5-ton motor lorry hitting a brick wall at 60 miles an hour. To prevent the guns from freezing and jamming above 30,000 feet, warm air from the radiator duct was channeled into the gun bays. The Spitfire Mark I-A was powered by a Rolls-Royce Merlin III, a 7.1-gallon liquid-cooled V12 engine. The engine weighed approximately 1,440 pounds. Its 12 cylinders were arranged in 2 banks, set at a 60-degree angle. The cylinders were cast as single pieces with the blocks and heads formed together. Each cylinder had 4 valves, 2 for intake and 2 for exhaust. The engine was supercharged, and the supercharger spun at over 8 times the crankshaft speed, forcing the fuel-air mixture into the cylinders under pressure. The engine used a carburetor with a float chamber, causing a critical weakness in the Spitfire. In normal operation, fuel flowed into the chamber through a valve. A brass float rode on the surface. When the fuel level rose, the float rose with it and pushed the valve shut. As the engine consumed fuel, the float dropped and reopened the valve, exactly like a household toilet cistern. A narrow section of the intake pipe then created a low-pressure zone that sucked fuel into the cylinders. This created an issue during negative G maneuvers in combat, such as pushing the nose down sharply to dive. In negative G, fuel surged to the top of the chamber. The float rose with it and shut the fuel valve, cutting the fuel to the engine. The Bf-109, in contrast, used direct fuel injection and was completely unaffected by negative G. If a Spitfire was on its tail, a German pilot could simply push the nose down to escape. If a Spitfire tried to follow the same way, its engine would splutter and lose power. When the Spitfire returned to level flight, the empty chamber caused the valve to open too wide, flooding the chamber with fuel. A small metal restrictor developed by engineer Beatrice Schilling was later fitted to the fuel line. It couldn't prevent the initial cutout, so pilots learned to enter a half roll before diving. But it did stop the engine from flooding when positive G returned. The Merlin's cooling system used pressurized water and ethylene glycol. This allowed the engine to run hotter without boiling, which meant a smaller radiator and less drag. 2 magnetos provided ignition. The 12-cylinder engine had 24 spark plugs. Each magneto fired plugs on opposite sides of the cylinders. If one magneto failed, the other continued to provide a spark to all 12 cylinders. The crankshaft went through the gearbox and drove a 3-blade, 2-pitch propeller. The Spitfire Mark I-A ran on 100-octane aviation fuel. This high-grade fuel pushed the engine to run at higher pressures without fuel igniting prematurely inside the cylinders. The engine consumed approximately 82 US gallons of fuel per hour at maximum continuous cruising power. Fuel was stored in 2 tanks stacked one above the other in the fuselage between the engine and the cockpit. The upper tank held 57.6 US gallons and was gravity fed. The lower tank held 44.4 US gallons. The combined capacity was 102 US gallons. Initially, both tanks were unprotected and posed a severe fire hazard if hit. To counter that, the lower tank was later covered with self-sealing material that would swell and close bullet holes. The upper tank was protected by a thin aluminium alloy cover, designed to deflect angled shots rather than self-seal. The fuel gauges operated only when a push button was pressed to prevent electrical wear. The pilot could manually shut off the fuel to minimize fire risk during forced landings. At maximum cruising speed, its range was 415 miles. Under combat conditions, though, the effective operational radius shrank to just around 130 miles. The Spitfire's cockpit was famously narrow. The fuselage was designed to minimize frontal area and reduce aerodynamic drag. Every inch of width that could be removed was taken out. That meant the cockpit was squeezed tightly around the pilot's body. Pilots described it as wearing the aircraft rather than sitting in it. The seat width was only 16 inches, less than the seat of a classic London double-decker bus. Broader pilots would find their forearms brushing against the metal walls during flight. Pilots entered through a sliding canopy and a folding side door on the port side. Behind the seat, 75 pounds of steel armor plating was bolted in place. To compensate for the rear visibility that the headrest and armor blocked, a rectangular rear-view mirror was mounted on top of the windscreen. It was a narrow view, but in combat, it was often the difference between life and death. The central instrument panel contained the rate of climb indicator, artificial horizon, airspeed indicator, turn indicator, direction indicator, and altimeter. A compass was mounted below the main panel between the pilot's legs. The right-hand panel displayed engine information. The top row housed the engine speed indicator and boost gauge. Below these were temperature and pressure gauges for the radiator, oil, and fuel systems. The left-hand panel contained auxiliary systems, including the oxygen regulator, undercarriage position indicator, and brake pressure gauge. The control column, designed by the Dunlop tire manufacturer, had an unusual circular spade grip. Near the top, there was a hinge, so only the upper part moved from side to side to control the ailerons. The gun button was on the top left of the grip, with a brass safety ring that could be twisted between safe and fire positions. The brake lever was fitted to the back of the spade grip handle, allowing the pilot to operate it while maintaining a firm hold on the flight controls. The bar and Stroud reflector sight was mounted above the center panel. To ensure its continued operation, 3 spare lamps for the reflector sight were stowed in dedicated holders located on the right-hand side of the cockpit. The port wall housed the throttle quadrant, propeller pitch control, and trim wheels. The starboard wall held the undercarriage selector and fuel cocks. The rudder pedals featured 2 footrests. The upper step was positioned 6 inches higher. During combat, pilots used this upper step to raise their legs into a more horizontal posture, increasing G-force tolerance by at least 1 G. Before starting the engine, the pilot worked through a systematic checklist. The fuel cock levers were turned to the on position. The throttle was set to just half an inch open. The mixture control was pushed to rich, and the air screw pitch lever was pulled back. The radiator flap lever was pushed forward to open to prevent the engine from overheating during warm-up. The pilot then checked the undercarriage. The selector lever had to be confirmed in the down position, and the green indicator light on the instrument panel had to be illuminated, confirming the wheels were locked down. There was also a mechanical backup. When the wheels were locked, small red-tipped metal rods protruded up through the surface of each wing, visible directly from the cockpit. Before calling for the start, the pilot flicked the 2 magneto switches to on, then reached to the bottom right corner to switch on the starting magneto. The hand priming pump was pumped until the pilot felt a sharp increase in resistance, a sign that the fuel lines were primed and ready. The pilot shouted, "Contact," and pressed the starter button. As the engine began to turn, the pilot pumped the priming pump rapidly in sync with the starter. On a warm day, 4 strokes were enough. In winter, it could take as many as 13. The Merlin engine burst into life with a huge, massive roar and flames spitting from the exhaust stacks. Taxiing required constant vigilance. The long nose angled upwards and blocked forward visibility almost completely. The pilot had to zigzag across the airfield to see the runway ahead. The narrow landing gear track made the aircraft wobble on uneven grass. It felt unstable with a constant risk of scraping a wingtip on the ground. Before opening the throttle, the pilot set the rudder trim to fully starboard to counteract engine torque. The throttle was opened gently but firmly, after which the engine torque would immediately push the nose violently to the left as the plane lurched forward. As speed built, the pilot pushed the stick forward to lift the tailwheel off the ground. This leveled the aircraft and finally allowed forward visibility. The Spitfire lifted off at approximately 75 to 85 miles an hour. Once airborne, the pilot moved the undercarriage selector lever to the up position. The engine-driven hydraulic pump then automatically raised and locked the wheels. When the cycle was complete, red indicator lights on the instrument panel confirmed the gear was up and locked. In flight, the controls were described as light as a feather. The aircraft responded almost telepathically to small inputs. The Spitfire could outturn nearly anything in the sky. In a typical Battle of Britain engagement, a Bf-109E would attack from above using altitude and the position of the sun to reduce the chance of early detection. A Spitfire pilot would see the fighter only at the last moment as a brief movement in the rearview mirror and would turn hard before the German pilot could close to effective firing range. If the Bf-109 tried to follow, the Spitfire would be able to hold the turn clean, wasting no energy. The German pilot's gun sight would not be able to settle, and the attack would lose momentum. The Bf-109's limited fuel supply would not allow it to stay turning in the circle for too long. When a German pilot broke away to prepare for another attack, a Spitfire pilot would be able to see that movement and react to it. The Spitfire would then tighten its turn to force the overshoot. As the German fighter passed in front, the Spitfire would turn the other way and move in behind it. That would change the Spitfire from the aircraft being chased into the one doing the chasing. From there, the Spitfire pilot could fire a long burst. Most of the bullets would hit the outer skin of the German aircraft and cause only small flashes and surface damage. If an incendiary round hit near the wing root or fuel system though, it would cause a brief flash and then a line of flame trailing back in the airflow. Escaping fuel would make the fire spread quicker. A damaged Bf-109 would be left with no choice but to turn away towards the English Channel. British pilots called the Spitfire a lady in the air, but a bitch on the ground. The long engine cowling and high nose-up attitude limited forward visibility to almost zero during approach. Pilots configured the aircraft for landing using a specific sequence. Before beginning the approach, the pilot reduced speed to 140 miles an hour, locked the canopy open, set the emergency door to half cock, and raised the seat to the highest position for better visibility. The undercarriage selector moved down. Green indicator lights confirmed the gear was locked, along with mechanical rods that protruded from the wings. The mixture was set to rich. The propeller pitch control moved fully forward to fine pitch and high RPM, ensuring maximum power was available if the pilot needed to go around. The flaps lowered to the fully down position at 90 degrees. Rather than fly in a straight line to the runway, pilots flew what became known as the Spitfire curve. It was a long, continuous arc from the downward leg all the way to touchdown, keeping the runway visible through the side of the canopy. The recommended approach speed was 85 miles an hour for an engine-assisted approach, or 90 miles an hour for a glide approach. The goal was a three-point landing with the main wheels and tail wheel touching simultaneously at around 65 to 75 miles an hour. If the approach speed was slightly too high, the aircraft would float over the runway. Due to the center of gravity and sensitive brakes, excessive braking after touchdown could tip the aircraft onto its nose. The Spitfire Mark I-A became the only British fighter to remain in continuous production throughout the entirety of World War II. The Mark I variant alone saw 1,567 units built between April 1938 and March 1941. Britain entered the war short on experienced fighter pilots and was facing an opponent that had mobilized earlier and carried significantly more combat experience into 1940. The Spitfire's forgiving handling, pilot armor, and self-sealing tanks gave even inexperienced pilots a fighting chance against a more seasoned enemy. As the ace sailor Merlin said, the Spitfire had style and was obviously a killer. You could dive till your eyes were popping out of your head, but the wings would still be there. She had no vices. She was beautifully positive. The Spitfire was mainly built in Southampton. During the 57 air raids of the Southampton Blitz, the Luftwaffe destroyed the factory and left the city in ruins. But this didn't stop production, which had been spread around the country. Now, after almost 90 years, a monument is planned in Southampton to honor the Spitfire as a symbol of resilience and beauty. It will commemorate the aircraft and the people who kept working through the bombing. You can be part of that legacy and click the link in the description to support the building of the Southampton Spitfire Monument in honor of one of the most beautiful planes ever made. Thank you for watching. If you spotted any errors, please let us know in the comments. We're looking to continuously improve. If you'd like to learn more about the Spitfire's most lethal adversary, check out our video on the BF-109.